Good day everyone, welcome to this session looking at the design of tension members, and we're specifically going to be going through the code requirements for tension members, trying to understand the clauses so that the calculations and requirements make more sense. And then you can also see what you're required to know as part of this course, and all of what we're going to be doing now is taken specifically from SANS 10162 Part 1, our hot rolled steel design code. So make sure you have your copy, and much of what I am going to be showing you now, giving you now, I would encourage you actually to write that into your code. So as you have a clause, the clause may make more sense because you have the sort of some guideline or sketch or something there alongside it to help it make sense. Now, here we're going to first start off with some requirements, and one of the things that we need to start checking with tension members early on is something called the slenderness ratio. And so when it comes to this, is that the slenderness ratio of a member in compression shall be taken as the ratio of the effective length, KL, to the corresponding radius of gyration. So slenderness is KL over R. And this item slenderness will come up quite often when you start designing compression members. So just be aware of it. We will go through what is R quite a bit more in sort of from a practical perspective in compression members. But radius of gyration, remember that should be square root of I over A. Otherwise you can view it as sort of the average distance of material from an axis. That's not a perfect definition, but you'll see why when we do compression members. And then the length of our member, and then our effective length factor. And so K for tension elements is normally 1. Normally for most tension elements we look at, it is taken as 1. And it could be other things though, especially for compression elements or fixed ends, etc., etc. Now, the ratio member of tension, the slenderness ratio of a member in tension shall be taken as the ratio of the unbraced length to this corresponding radius of gyration. So you can see, as I was mentioning now, tension you pretty much take as 1, unless you have a very good reason not to. Now, for compression members, we limit KL over R to 200, and for tension, we limit it to 300. So KL over R must be less than or equal to 200 in compression, and KL over R is less than or equal to 300 in tension. And this limit may be waived if other means are provided to control flexibility, sag, vibration, and slack in a manner that is commensurate with the service conditions of the structure, or it can be shown that such factors are not detrimental to the performance of the structural assembly of which the member is a part. That you could view as a polite way of saying that you can kind of violate the requirements if there is reason for it. What will happen if you have a very long, thin member, for instance, a cable on a cable-stayed bridge or something like that? You may easily violate this KL over R limit of 300. It doesn't mean it's going to fail. It doesn't mean that it's suddenly going to lose strength. What will happen for very slender members, they may vibrate, they may sag, also they just kind of look silly on site. You have these spindly little members. You may have practical issues with during erection, construction, etc. So normally you want to stay away. It's not a it's a code requirement, but to be honest, if you didn't quite get it right, it wouldn't be sort of detrimental per se. So as I said, yeah, so there's your limits of 200 and 300. But now let's continue on with code requirements. And you'll see I'm jumping between clauses, so just have a look at the number as we go. Axial tension and connection resistance, so there is our tensile resistance. The factor tensile resistance shall be, and so we've got 3 specific requirements here that we have to test for. You've got gross failure of the section, you have then net failure, net resistance, I'm just going to write that again, and then this is your net resistance, and then you've got A primed, this is effective net area, effective net. And so that is the total area, the gross. The net is the area minus any cross-sectional holes, and then the effective net is minus cross-sectional holes, also allow for shear lag. allow for the fact that you do not have all the sections connected, and so we will then have a look at what is the definition of shear lag, etc. So gross, net, effective net that you will then need to be able to design for. But one thing, just as a note, only check number 3 if shear lag occurs. If shear lag occurs. What you will find is if there is shear lag, if not all the parts of a section are connected, the shear lag resistance, this third one, will always be less. So you don't have to go calculate the second one because it'll obviously be more. So lastly then, for pinned connection, so this is for a single bolt in flat plate kind of idea. It's a pure pin, single bolt dowel type connection. Those are not common, but there are guidelines for that if you have a single point that you connect. Normally you have 2 or more bolts that you'll use in terms of your connection design. And so now, just to remember in terms of details, you've got your Fy, which is yield, and your F subscript U, which is your ultimate tensile strength. And so, just as a bit of a background, looking at how you might get those if you're not familiar with the process, what I've got shown here is actually a test specimen from a test done earlier today in our lab. This is actually on high tensile steel. This was a 550 MPa material, well that's specified, was put in the lab, and then a dog bone was made, so you clamp it each side and then you pull on it and then it elongates and elongates until it fails. And this actually failed at about 660 MPa, because one thing you must remember from earlier lectures, your specified steel strength, for instance a 355 MPa steel, that is what the minimum with a certain percentage probability that's allowed to land on site. The average material strength should be above this. So this is specified as a 550, but what we actually tested was 660. It was quite a bit stronger than the supplier said, and it was loaded, and it would got to a point it yielded, especially this thinner section in the middle. At that point it would have started elongating, and then soon after that it got to fracture. And this is actually ultimate strength that it got there, and then it necked and it broke, and we ended up then with a failed section. So that's just looking back at ultimate, the ultimate stress and the yield stress, which is then ultimate is also your fracture stress. Okay, now once we have those equations for calculating, let's see how to do that. So firstly we're going to have a look at net area and effective net area in terms of cross-sectional areas. And I'm going to draw a sketch at the side here that will hopefully assist in terms of trying to visualize this, and also it's useful having these definitions next to your notes. So here we're going to take an angle and we're going to fold it out. So this is the total width, and along this dashed line is that I've just taken the angle and I have folded it flat, and this will be a total width WN. And for instance, we will have 4 bolts, and there will be various failure patterns that are possible with these bolts. And the important dimensions to note, for instance, are S and G, the pitch and spacing between the bolts. And so now, normally your effective area for a segment normal to the force and direct tension, your effective area is your net areas, apologies, your that's W, and your net area is when you take off the bolt. You would subtract the diameter of the bolts from those. So so AN of each segment along a potential path of minimum resistance calculated as follows. For segment normal to the force, so we've got our force pulling on there. And so now for segment inclined to the force, and this is talking about segments, so we'll just add it up. You add on a little bit of extra material. So if you are dealing with that piece there, it's between the bolt holes, so you subtract the bolt hole off. But what we do is we convert a horizontal distance g. So this would be, for instance, g times t. If I was just working on this green section, this would be g times t plus s squared times t over 4g. That would be then my green section. I would still have to add on more outside of it each side. So this would just be for a segment, and then we would add on more on top of that. So always remember, when you're working with something, if you take a width, multiply it by a thickness, it's very easy to forget to multiply it by the thickness of the steel, and then you add on a little bit extra. Because there's a diagonal, it's a bit longer, so you add on this s squared over 4g times t, and that, to be honest, is a bit of a approximation, just to make sure that you have a little bit of more area and account for what's going on there. Now, in calculating Wn, the width of the bolt hole shall be taken 2 mils larger than the specified hole diameter. Where it is known that drilled or punched in drills holes will be used, this allowance may be waived. So what does that mean, and why do we care? If you have a bolt, here's your bolt. This has a normal certain outside diameter, d, that needs to fit through your hole. And so, if you have a drilled hole, the actual hole that you will have there you need to put into your member is d plus 2 mils. So then you will have a hole here. I'm exaggerating this quite severely. This would be your d primed. But if it's punched, if they have a machine that punches it and just punches out the hole, you can get a little bit of damage around the edge, and so maybe you're going to lose some more cross-sectional area. So your effective area is actually d plus 2 mils plus another 2 mils to allow for the damage due to the punching. And so you consume punched for a thickness, for T less than 12 mils, T less than equals 12 millimeters. You don't know what's going to happen in the workshop, and so this is just an approximation, and you may be wrong at times, but in general this should be more than sufficient. So drilled holes take a D plus 2, and this is the physical size. So if you have an M16 bolt, e.g. M16, that means it's a 16 mil outer diameter, which means you will make that 18 millimeter hole. So there's 1 mil tolerance all the way around the bolt, so you can fit it in the hole. And then, especially when you're lining up different plates. But you subtract an extra 1 mil around that, i.e. 2 mils total, if it is a punched hole. So that is that clause. Now, that then will help us in determining an effective net area when there's a bit of damage. So we now need to consider the influence of shear lag. And so firstly we need to see now, when does shear lag occur? Because we need to have a look at what is an effective shear area. And so firstly, when will we get shear lag? And so you've got this clause here, 12.332. When bolts transmit load to some but not all of the cross-sectional elements, and only when the critical net area includes the net area of unconnected elements, the effective net area shall be taken as follows. So what does that mean? Well, I'm going to show you what it doesn't mean first. So let's say now we have a cross-section. We have a channel, a parallel flange channel, let's say, and we have an angle, and we have an I-beam, and we now need to connect them together on site. We want to make sure force is transmitted through all components of those. So if we now put bolts into this, if we put a bolt there and there and there and there is no shear lag. All components, both flanges and the web, are carrying load. If we put a bolt there and there, then all components of the angle are carrying it. There is that going to give you shear lag? Yes, because the web is not connected. needs to be a distance over which the load spreads out. There is no load initially spread into that web. If I add some bolts there, yes, then none of these will have shear lag. So these, when you have no shear lag, so then you don't need an effective net area. So no any primed. There is no loss due to shear lag. There's no loss because the load has to distribute across the section. So now, this clause here, 12.332, is when you do have shear lag, when there aren't bolts through all components, where something's unconnected, so there needs to be a distance to transmit the load into that section, and let's see how we do it. So firstly, be very careful with these clauses and just read them, because they get a little bit confusing, especially when there's double negatives and all these sorts of things, and not often written in the clearest way. For all sections with I or H shapes, okay, great, so if I've got an I or H beam with flange widths not less than 2/3 the depth, so not less, so i.e. greater than 2/3 the depth, and for structural T's cut from these sections when only flanges are connected with 3 or more transverse lines of fasteners. So that was a whole bunch of clauses that just came up there, but to simplify it, if you have a I-beam or H section and it has a width of BF and then a height of H, the breadth of your flange needs to be greater than or equal to 2/3 of the height. Then you also need to have bolts, 3 or more. Then it satisfies the clause, and then you will be able to use 90% of the effective area, 0.9 times the effective net area, so area minus 4 bolts. And then you can use 90% of that area. So that's a very effective section. So that is a good thing. And think about it this way: you want a narrow section. When this H value is small, there's less shear lag because there's the load kind of distributes easily into it. And so that kind of makes sense. You want broader flanges connected and then smaller, thinner web. Now, one of the things that comes up every year, multiple times, is this area of transverse lines of fasteners. I have explained this in other videos, but just in case, I am going to add this again here, simply because it's amazing how many times this question has to be answered. So for instance, here you have an angle, and it has, let's say, 1, 2, 3 bolts there, and then it's got 2 lines. And now just start thinking about, is this 2 lines of transverse bolts or 3 lines? Well, you want load to distribute out into the section, so you want more length. You want as much distance as possible for load to distribute out. So this is 3 transverse lines of fasteners. And whether there's 1 row or 2 rows, it doesn't actually make a difference in the code. It's the fact it's what is this distance along there, and then we quantify that by number of bolts. There are more accurate ways to do this in the American and European codes, but for now we've got fairly simplified guidelines. So coming back now, if for instance now we have angles connected by only one leg with 4 or more transverse lines of bolts, so I would need to have another one there and there. Now I've got 4, and fewer than 4 I will have different effective area. So either I use 80% of the effective area or 60% of the effective area. So you can see that the cross-sectional area decreases. Then for all other structural sections connected with 3 or more transverse lines of fasteners or 2 lines of transverse fasteners. So this, for instance, would be your PFC sections, your parallel flange channels, your C sections, your channels, your cold formed lip channels, your and then, oh, sorry, then H and I sections. No, but you told me H and I sections were covered above with your breadth of flange less than 2/3 of height, etc. So this clause applies to all these other sections. So that looks at effective net area. Now let's go on to looking at effective net area when there is tension. And we come to this clause here. Now, the very simple thing that you need to do with this clause is just delete it because it's actually wrong. I don't know if it's just a mistake in the code or what, but or I'm just misunderstanding what they are, trying to define. But I'm going to write out hopefully an easier way to use it, and you will see why now that we are going to write it in a different way. So effective net area is ANE1 plus ANE3, and you'll see what ANE1 is, so it's two different areas, when there's a transverse weld, or minimum of ANE1 plus ANE3, and then ANE2 plus ANE3, ANE2 plus ANE3. And you'll actually see, you could also either just have minimum of ANE1 and ANE2 plus ANE3, whichever, you'll get the same answer. So this is the area of an angle that has been welded to something, and you now need to work out the cross-sectional area. And I'm going to do a sketch now which may help you understand this. So here's my sketch we're going to be using to try understand the effective net area of a welded member. And I've drawn actually quite an unusual shaped section. This is not an angle, but if I drew it as an angle you may miss a concept. So I've intentionally drawn it as some sort of funny asymmetric T-section. And we now need to work out different areas. So firstly, we've got for elements connected by a transverse weld, ANE1 equals W times T, and otherwise I'm going to write that as ANE1 equals W1 times T1. So this is this effective area, or this total area at the bottom, and when it says transverse weld, that's an area all the way along the edge. So if we put a weld there, this end is totally effective. It will be have all the load distributed. It will be fully effective, and there we go. Now, for elements connected by longitudinal webs along two parallel edges. So we've got longitudinal connections down the length, so that means we've got a weld each side of length L. When L is greater than 2W1, and you can just put, I'm intentionally putting 1 and 2 so you can see there's a difference between outstand and connected length. Your ANE2, where otherwise you can write this W equals W1 here, and then T equals T1, or you can just put those in there. You can otherwise just go W1 and T1, depending on which one makes more sense for you. And so this is a area when there's effective, there's loss of area due to shear lag. The fact that this is short means that the load's not fully distributed along the section, and so we then have an effective net area, ANE2. So ANE1 and ANE2 are the same thing. They're both this blue area, and either it's the total area or it's less than that. For a long weld for length than twice the width, it'll be most of that area. When W is greater than L, then you have that value, and so either it's quite a lot or a bit less. So it progressively decreases as the weld gets shorter, more of, or less of the total area is effective. Now, for elements connected by a single longitudinal web, single longitudinal weld. So this is this green area. It's everything sticking outside of the blue connected area. And so when L is greater than W, you need to start looking at how to calculate this. You've got an ANE3 value here, where the ANE3 is the area, that green area, adjusted for shear lag as well, so it will be less than that total area. And so we first need to work out what is the distance from the base where the weld is. So what is the distance from this sort of plate where the which is it's welded to the middle of the green area. And that's why this X bar, you've just got to be careful with, X bar equals, and now it's W2 minus T1 divided by 2. So that's half the height of that green area plus T1. And so that gives you the X bar, the distance from the connected plate to the middle of the green area. And so now the W value here you use is W2 minus T1, because we're dealing with these green areas. And so this will give you that green area plus minus a bit more depending on the length of the weld, adjusting for shear lag. So once you have those, you've got an ANE1 or 2 plus ANE3. That's why you can't add in ANE1, ANE2. That's the same cross-sectional area. You're going to have more steel than there is steel as part of the angle. So that will help you then determine the cross-sectional area, this effective net area adjusted for shear lag that I showed you just now. And hopefully putting those different labels on it will also make you have a look at the connected leg and the unconnected leg. So following on that, there are various code requirements that are put here to try guide you along the way. So go have a look through. But hopefully that should give you an idea of how to apply the code requirements to a tension element, either a bolted or a welded one, and what is the sort of fundamental reasons we are doing some of the things we are. Thank you.